For as long as we have looked at the sky, we have wondered how it began. Modern cosmology tells us that the universe was once hotter, denser, smaller. It expanded. It cooled. It formed stars, galaxies, planets. This early brilliant phase is called the Big Bang. But the Big Bang is not, strictly speaking, an explosion. It is a description of an early state of the universe. And once that is understood, a quieter question begins to emerge. If the Big Bang describes an early phase, what, if anything, came before it? Tonight, we will explore that question gently. There is nothing to solve, nothing to decide, only ideas to drift through. Let your thoughts move slowly as we travel backward, not through space, but toward the edge of time. The phrase Big Bang often carries the image of a sudden explosion. But in modern physics, it means something more precise. It refers to a hot, dense, early universe that expanded and cooled. Not matter exploding into empty space, but space itself expanding. Observations support this model with remarkable consistency. Galaxies are receding from one another, their light stretched by expansion. The cosmic microwave background fills the universe, a faint afterglow of an earlier, hotter era. Light elements, hydrogen, helium, traces of lithium, exist in proportions predicted by early universe calculations. When Einstein's equations are traced backward, they lead toward a state of extreme density and curvature. Classically, this becomes a singularity. But most physicists do not interpret this singularity as a physical object. It signals that general relativity, our classical theory of gravity, has reached its limit. At extreme densities, quantum effects cannot be ignored. The equations stop giving meaningful predictions. The beginning may therefore represent not a true origin, but the edge of a theory. And so the question shifts. Not simply what happened at the beginning, but whether the beginning, as we imagine it, is even the right concept. To ask what came before the Big Bang is to assume that time itself existed beforehand. But what if time is not external to the universe? What if time is woven into space-time itself? In general relativity, space and time are inseparable. Space-time curves in response to energy and matter. If space-time has a boundary in the past, there may be no earlier moment beyond it. Some cosmologists compare the question to asking what lies north of the North Pole. The concept breaks down at the boundary. Stephen Hawking argued that even if something existed before, it might leave no observable imprint. And physics concerns itself with what can, in principle, be observed. The no-boundary proposal suggests that the early universe may be finite, but without an initial edge. In certain mathematical formulations, time transitions smoothly from a timeless Euclidean phase into the flowing time we experience. In such a model, there is no sharp moment of creation. There is no dividing line between before and after. Instead, time emerges. And once time is emergent, the word before begins to dissolve. While some models question the meaning of before, others suggest that the Big Bang was not the ultimate beginning at all. According to inflationary cosmology, the universe underwent a period of accelerated expansion before the hot Big Bang phase. Inflation smooths and flattens space. It stretches quantum fluctuations into cosmic structure. When inflation ends, its energy decays into particles and radiation. This reheating phase becomes the hot Big Bang we recognize. But inflation itself may not be eternal in the past. The Borguth-Vilenkin theorem shows that many inflationary spacetimes are past incomplete. This suggests inflation may require its own origin or prior state. Some models propose eternal inflation, where inflation continues in distant regions. In that picture, our observable universe is a bubble within a much larger inflating background. Each bubble has its own hot Big Bang. Before our Big Bang, there may have been an inflating parent spacetime. But in such a multiverse, before becomes relative. Each region carries its own time coordinate. The question grows more subtle. Before, for whom? If inflation may not have been the ultimate beginning, another possibility emerges. Perhaps the universe did not begin from nothing at all. Perhaps it was once contracting. In Bounce cosmologies, the Big Bang is not a birth but a turning point. The universe shrinks, grows denser, approaches extreme conditions, and then reverses. Contraction becomes expansion. The Big Bang becomes a big bounce. In such models, time does not begin at the bounce. It flows through it. The singularity predicted by classical equations is replaced by new physics. Some versions describe a slow, smoothing contraction called an ekpyrotic phase. During this phase, irregularities are flattened. Anisotropies are reduced. The universe becomes orderly before expanding again. Other versions arise from higher dimensional ideas. In certain string-inspired models, our universe is a three-dimensional brain floating in a higher dimensional space. Two such brains may approach one another. Their collision releases energy. That energy becomes what we perceive as the hot Big Bang. In this picture, the before is not empty. It is another configuration of space and matter in higher dimensions. Time continues. It does not begin. And if a bounce occurred once, it may have occurred many times. Some cosmologists extend the bounce idea further. They imagine not one contraction and expansion, but many. A cyclic universe. In this scenario, the cosmos expands for trillions of years. Galaxies drift apart. Dark energy dominates. Expansion accelerates. Eventually, conditions shift. Expansion slows. Contraction begins. Density increases once more. Another bounce follows. Another expansion. Each cycle may last longer than the entire history of our observable universe. There may have been countless cycles before ours. In some cyclic models, entropy grows with each cycle, but is diluted by expansion. In others, entropy is handled through subtle gravitational effects. Time stretches backward, not to a single beginning, but to an endless sequence. The question of before dissolves into recurrence. There was no first moment, only rhythm. Roger Penrose proposed a different form of cyclicity. Not through contraction and bounce, but through transformation. In conformal cyclic cosmology, the universe proceeds through successive aeons. Each aeon begins in a hot, dense state. Each ends in extreme expansion, where galaxies are separated by unimaginable distances. Over vast spans of time, black holes evaporate. Massive particles decay. Only radiation remains. When only radiation exists, scale loses meaning. Distances become irrelevant because mass defines scale. Under a conformal transformation, the infinite future of one aeon can be mathematically mapped onto the Big Bang of the next. In this view, the remote future becomes the next beginning. There is no singular first creation, only aeons. Penrose suggested that subtle imprints from previous aeons might appear in the cosmic microwave background. Circular patterns have been proposed. These claims remain debated, but the idea remains elegant. The universe does not begin once. It renews. At densities near the Planck scale, classical space-time may cease to behave continuously. Quantum gravity attempts to describe this extreme regime. In loop quantum cosmology, space itself is quantized. Geometry has discrete structure. When the universe contracts to extremely small size, quantum effects generate a repulsive force. The collapse halts. A bounce replaces the singularity. Before expansion, there was contraction. Before contraction, perhaps expansion again. Other approaches treat the universe as a quantum wave function. In such frameworks, the universe does not evolve from a point. It exists as a superposition of possible geometries. Time may emerge from correlations between quantum states. Some proposals describe the universe tunneling from a quantum vacuum. But this vacuum is not absolute nothingness. It is a lowest energy state within a framework of physical law. Nothing becomes a technical term, not emptiness, but structured possibility. In these models, before the Big Bang, may have been a quantum phase without classical time. any model that reaches beyond the Big Bang must confront entropy. The early universe had remarkably low entropy. As the universe evolves, entropy increases. This gives time its direction. From ordered past to disordered future. If there was a bounce, did entropy reverse? Did time flow in opposite directions, on either side? Some symmetric models suggest two universes emerging from a common low entropy state, time flowing outward in both directions. Others maintain a single arrow, continuing smoothly through a bounce. In cyclic scenarios, entropy must be diluted or reset. Penrose argues that gravitational entropy plays the central role. Low gravitational entropy at each beginning sets the arrow of time. Whether time's direction is fundamental or emergent remains uncertain. But any answer to what came before must explain why the early universe was so ordered. The observable universe extends back to a time about 380,000 years after the hot Big Bang. Before that, the universe was opaque plasma. Earlier still, nuclear reactions shaped light elements. Earlier still, inflation may have occurred. But before the Planck time, our current theories cannot speak with confidence. No telescope can directly observe what happened at that scale. We rely on indirect evidence. The spectrum of primordial fluctuations. The polarization of the CMB. Searches for gravitational waves. Some bounce models predict specific patterns in fluctuations. Inflation predicts a nearly scale-invariant spectrum. So far, observations favor inflation. But absence of evidence is not evidence of absence. Future measurements may rule out entire classes of models or reveal new anomalies that reshape the picture again. For now, the pre-Big Bang era remains a frontier defined as much by mathematics as by measurement. Long before modern cosmology, philosophers asked similar questions. Did time begin? Or has it always existed? Steady-state cosmology once proposed an eternal universe with matter continuously created. The discovery of the cosmic microwave background shifted scientific consensus toward a hot early phase. The term Big Bang was coined somewhat dismissively, yet it endured. Augustine argued that time began with creation. Modern physics echoes this possibility in certain interpretations. The Copernican principle reminds us that we occupy no special place. Perhaps our beginning is not unique. Perhaps it is one transition among many. There is no single accepted answer to what came before the Big Bang. Some models posit an actual prior phase. Others deny that before has meaning. All must agree with known data. Many rely on physics, not yet experimentally confirmed. Observers inside the universe may never access direct information about pre-Big Bang epochs. Yet exploring these possibilities sharpens our understanding of time, causality, and singularities. It forces us to examine what we mean by beginning. Perhaps the deeper insight is not a specific model. Perhaps it is humility. The realization that our equations describe only part of the story. When people say the Big Bang, they often imagine the very beginning. But in modern cosmology, the phrase has become more precise. Many scientists now reserve hot Big Bang for the hot, dense plasma phase of the universe after an earlier event. That earlier event is called cosmic inflation. Inflation does not replace the Big Bang. It reshapes what we mean by the beginning. Cosmic inflation proposes that the very early universe underwent a period of extremely rapid exponential expansion. Space itself expanded. Distances doubled again and again in tiny fractions of a second. This expansion is modeled as being driven by a scalar field called the inflaton. The inflaton's nearly constant energy density acts like a repulsive gravity. In effect, it produces a de Sitter-like expansion. During inflation, quantum fluctuations of the inflaton and space-time were stretched from microscopic scales to cosmic scales. These tiny fluctuations later became the seeds of galaxies and large-scale structure. Inflation explains why the universe appears nearly flat, nearly homogeneous, and nearly isotropic. It also explains why we do not observe heavy relics like magnetic monopoles. In modern usage, inflation comes first. The universe begins in a vacuum-dominated state, expanding exponentially. Then inflation ends. This ending is called reheating. Reheating converts the inflaton's energy into ordinary particles and radiation. That conversion creates the extremely hot, dense conditions, traditionally called the Big Bang. So when cosmologists say inflation precedes the Big Bang, they mean that vacuum-driven expansion happens first and its end initiates the hot plasma phase. The beginning becomes a transition, not an explosion, but a change of state. Before inflation was proposed, the standard hot Big Bang model faced puzzles. One was the horizon problem. The cosmic microwave background has almost exactly the same temperature in all directions. Yet in a non-inflationary universe, regions more than about 2 degrees apart on the sky were never in causal contact. Light could not have traveled between them. So how did they reach the same temperature? Inflation offers an answer. Before inflation, the patch that became our observable universe was much smaller. All its regions could interact and come to thermal equilibrium. Then inflation stretched that small equilibrated region to a size far larger than the observable universe. Regions now far apart were once close together. Uniformity was established before being expanded. In comoving coordinates, the horizon shrinks during inflation. Modes once inside each other's horizons are pushed to super-horizon scales. Another puzzle was the flatness problem. Observations show that the universe is extremely close to spatial flatness. The density parameter is very near 1. But in a decelerating universe, any tiny deviation from exact flatness grows with time. For the universe to be so flat today, it would have required extraordinary fine-tuning in its earliest moments. Inflation resolves this naturally. During exponential expansion, the scale factor grows enormously, while energy density remains nearly constant. The curvature term in the Friedmann equation is rapidly suppressed. A small patch becomes flatter as it expands, like a balloon surface, appearing flatter as it inflates. After about 60 e-folds of expansion, curvature is driven extremely close to zero. Even if the universe began noticeably curved, it would appear nearly flat today. Inflation also dilutes unwanted relics. If heavy particles like magnetic monopoles were produced in the early universe, inflation would expand space so dramatically that their density becomes negligible. Inflation also preserves large-scale smoothness, while stretching quantum fluctuations into classical density perturbations. Those perturbations seed galaxies and clusters. In one motion, inflation explains both why the universe is smooth on large scales and why it contains structure. Inflation makes predictions. One is a nearly scale-invariant spectrum of primordial perturbations. Measurements of the cosmic microwave background show a spectral index slightly below 1. This matches slow-roll inflation remarkably well. Inflation predicts perturbations that are predominantly adiabatic. Observations show they are overwhelmingly so. Inflation predicts near flatness. Measurements confirm spatial curvature is extremely close to zero. It predicts coherent acoustic oscillations in the primordial plasma. These appear as multiple acoustic peaks in the CMB power spectrum. Inflation also predicts that primordial fluctuations should be nearly Gaussian. Observations find them very close to Gaussian. It predicts a background of primordial gravitational waves. So far, only upper limits have been measured. These limits rule out some simple models, but remain consistent with many others. Collectively, CMB temperature and polarization data, large-scale structure surveys, and flatness measurements fit inflationary predictions better than known alternatives. And yet, no single inflation model has been uniquely confirmed. Inflation explains much, but not everything. current theory does not tell us. What started inflation? Some models treat inflation as the earliest meaningful phase. Others embed it within larger frameworks. Bounces. Eternal inflation. Multiverse scenarios. The physics that triggers inflation remains unknown. And so the question returns. What came before inflation? Stephen Hawking offered a different perspective. He argued that asking what came before the Big Bang may be physically ill-posed. His no-boundary proposal suggests the universe has no boundary in time. He compared it to the South Pole. You can go south until you reach the pole. But there is nothing south of the South Pole. Likewise, there may be no before the Big Bang in physical time. Hawking introduced imaginary time to smooth out the singularity. Near the beginning, the distinction between space and time blurs. Instead of a sharp starting point, the universe has a smooth, finite, boundaryless geometry. He argued that events before the Big Bang are not defined because they cannot be observed. In that framework, time begins with the Big Bang. The universe is self-contained. Its beginning is determined by physical laws and its quantum state, not by an external cause. Inflation does not remove the mystery. It moves it. The Big Bang becomes reheating. The beginning becomes inflation. The origin becomes the state that started inflation. And perhaps that state is part of a larger framework. Or perhaps, as Hawking suggested, before is not a meaningful word. Inflation takes a small, causally connected patch and stretches it into the vast cosmos we see. It smooths curvature. It explains uniformity. It seeds structure. It reshapes our understanding of the beginning. But whether there was something before remains open. Not empty. Not solved. Just open. And as we drift backward through expanding space, we find that the closer we move to the beginning, the more quietly the question itself begins to dissolve. And so we arrive quietly at the edge of time. The Big Bang may have been a transition, a bounce, a boundary, or the smooth beginning of time itself. Perhaps there was something before. Perhaps there was not. Perhaps the word before simply dissolves when examined too closely. The universe expands still. Galaxies drift apart. Stars are born and fade. And somewhere within this vast unfolding, the question remains open. Not empty, not silent, just open. As you rest now, let the beginning remain gentle. The universe does not hurry to answer, and neither do we.